Today we're going to be looking at another heavily requested NileRed video. Today we're going to be looking at real diamond water. We're making the world's most expensive carbonated water. As a nuclear engineer, I'm quite familiar with a lot of exotic forms of water that we use in various nuclear power plants, but diamond, this is a new one for me. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry, from engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's check it out.
My brother was reading a lot about the history of chemistry, and he was telling me about an experiment that he thought was really interesting. For this experiment, a diamond was placed in a jar with oxygen, and then it was heated up using sunlight and a really big lens. The diamond, which was nearly pure carbon, burned and combined with the oxygen, and the entire thing was converted to CO2 gas. This experiment was really important, and it helped confirm a few fundamental ideas and theories that were controversial at the time.
Good way to waste a diamond.
The thing that my brother found most surprising, though, was just the fact that it was possible to burn diamond, and when he told me about this, I had pretty much the same reaction. For some reason, we were always under the impression that diamond was basically indestructible, but that really isn't the case. To be fair, it's really hard and chemically resistant, but when it's heated until it's red hot, it can start reacting with oxygen. As we talked about this more, we joked about burning diamonds and then using that CO2 to make carbonated water. We thought that the idea of making carbonated water using diamonds was really funny and interesting, and if it worked, we'd kind of be able to drink diamonds.
I mean, you could use anything with carbon. I mean, graphite, graphene, coal. That'd be something, making it out of coal. That could be a different direction for the coal power industry.
Initially, it was mostly just a joke, but over the next few months, it slowly changed into something that I really wanted to do. I just had to know what it was like to drink diamond water. So I set out on a mission to make what was, to my knowledge, the most expensive carbonated water in the world.
This is basically reverse alchemy. Taking something valuable and making it into something that's not. Points for creativity.
To start off, I first had to buy some diamond. Large and high carat diamonds are of course extremely expensive and can easily cost
After all, it's just carbon.
Which is just slightly above the budget of this channel.
Slightly.
As the size goes down though, the price does as well, and after searching for a while, I found what I felt was one of the best deals. It was on eBay and it was offering 5 carats or 1 gram of nice and clean uncut white diamonds for $47.
Nice. That's good. I thought he was going to have to find some sort of really eccentric investor.
I definitely could have gotten this price lower if I went with even smaller diamonds or something like diamond dust, but I didn't want to go so small that it stopped looking like diamonds altogether. I thought that what I found was a good balance of size, quality, and price, but I'm not exactly a diamond expert, so I honestly have no idea if it really was a good deal. I did some rough calculations.
I'm not a diamond expert either.
I found that I probably needed about 4 grams, so I bought 4 orders from this listing. In total, this came out to be just a bit over $200, and it took about a week to arrive.
That's still cheaper than most diamond anything.
They all eventually showed up.
Very expensive for bottled water, though.
Which I thought looked oddly suspicious for some reason. The diamonds themselves were about as small as I had expected, and they looked like slightly oversized grains of sand. Despite being so small, though, they were still clearly diamonds, and they were actually able to sparkle a bit.
Cool.
Okay, so now that I had the diamonds, the first thing that I had to do was figure out how I was going to burn them to make the CO2. I probably could have tried recreating the historic way using a jar and a giant lens.
They almost look like those silica gels you see in those packets. If it wasn't for the shininess or their shape, they would almost kind of look like that.
But I just didn't feel like that was very efficient. Instead, what seemed like a much better idea was to heat them until they were red hot using something like a blowtorch, and then to pass oxygen over them. To do this though, I had to hold the diamonds in some sort of material that could both handle the high heat and the oxygen. Also, I ideally wanted it to be transparent so that I could see what was going on, and it seemed like glass was the only real option that I had. Regular glass would have melted though, including the lab-grade borosilicate stuff, so
really?
Instead, I had to try using something called quartz glass. Most forms of
Just
glass are
smash
made
it.
from silicon dioxide, but a bunch of other additives are included to lower its softening point and to make it easier to work with. However, quartz glass is nearly pure
That is
silicon
cool. Look at it
dioxide,
melt.
which gives it a much higher softening point. And hopefully, this should give me the ability to continually blast it with a torch without it bending or sagging. I looked online and I found
That is just really cool to see.
were commonly used in UV water sterilizers, and I found some relatively cheap ones on Amazon.
A lot of a lot of power plants, nuclear included, you see UV sterilizers and a lot of water for just critical cooling systems. But a lot of it's even like HVAC systems for, say, the instrumentation relays, not necessarily purifying the reactor coolant system, or sterilizing rather. I say purifying because it's usually lumped in at the end of a purification loop.
So, I ordered a few bigger ones, removed the ends, and cut them into roughly 9-inch sections. To hold the tube up, I just used a long glass rod, which let me hang it over 2 clamps. It wasn't exactly the most stable method, but it was just a test, so I didn't think it really mattered. The glass rod was also just regular glass, however, I figured that it would probably be okay. For the oxygen, I was originally just going to use those small red bottles that you can get from the hardware store, but they tend to be really overpriced. So instead, I went out and bought a proper full-sized oxygen tank. I also picked up a good quality regulator with it, which would give me much more careful control over the flow of oxygen. When I was ready to get things started, I loaded the tube with some of the diamond, and I blasted it with the blowtorch. Slowly, over about 30 seconds, the diamond started glowing red, and then I opened the oxygen regulator and I shot in a very gentle flow of oxygen. This caused them to glow even brighter, and they were now being slowly turned into CO2 gas. The quartz glass seemed to be working really well, but the rest of the glass was kind of a disaster. I thought that the glass rod would be okay because it wasn't getting hit directly by the torch, but that definitely wasn't the case. I also thought that using a glass pipette for the torch is pretty hot. Fine because
I mean, a torch can get up to, say, 2,000 degrees Celsius, whereas glass melts in the 1,500 range. So even if you're not right on top of it, can have some of that. It can be close enough that it can cause some unwanted thermal effects.
It wasn't touching anything, but again, I was obviously wrong. The air in the tube was apparently getting hot enough to start melting it, which meant that it was above at least 800 C. This was exactly why I had to use quartz glass.
Really, 800? Maybe I was way off, but the number I'm used to seeing is around 1,500. Maybe certain types of glasses are different. I mean, normally when you think of glass failure mechanisms, you're referring to the classic brittle fracture thing, and raising temperature can cause certain things like that to happen. Whereas if you go super hard on temperature quickly, then you can have melting before those before a more brittle fracture failure like that. But hey, I'm not going to argue. If 800's bad, 800's bad
for the tube. Otherwise, it all would have become a miserable and melted mess. So that run was pretty clearly a failure, and regular glass just wasn't something that I could use at all. I wanted to try again though, and this time, besides the quartz tube, everything else was metal. This run went way better than before, and after blasting it for just a few minutes, all of the diamond eventually disappeared. After doing all this, it was clearly possible to burn diamonds, but all the CO2 that I was making was kind of just being shot into the air. If I was going to be using it to carbonate water though, I had to somehow figure out a way to capture it. I thought about how to do this for a long time, and the easiest way that I came up with was just using liquid nitrogen. As the CO2 was made, I could pass it into a tube surrounded by liquid nitrogen, which should freeze the gas and turn it into dry ice. I had to first test this out though, and I started by filling a small dewar with some liquid nitrogen. Then after that, I dropped in a test tube, and I waited for it to cool down.
I remember being so fascinated by liquid nitrogen, especially when I was a kid. Just all these little experiments that you see people come to school do with, they just pour it out and seeing all the seeing how quickly it vaporizes. It's almost kind of spooky, like little Halloween fog coming in. Never really done a whole lot with liquid nitrogen at the nuclear plant. Rarely call for things that need to be cold, at least that cold.
I then got a flask, threw in a few pieces of dry ice, and attached some hosing to it.
I'm glad he's got the glove for dry ice. I mean, you still see dry ice being used sometimes in shipping containers. Fortunately, a lot of times it comes in like little bags and stuff, but if you've ever touched dry ice, you'll know exactly what I'm talking about.
With this setup, the dry ice was slowly turning back into CO2 gas and then traveling out through the hosing. When this gas is fed into the test tube, though, it should be able to freeze the CO2 and turn it back into dry ice. This was exactly what happened, and the moment that it was added to the tube, a cloud of dry ice started forming. The liquid nitrogen also started boiling a lot more, and I just left it like this for several minutes. After that, I pulled out the hosing, and there was a huge chunk of dry ice that had formed around it.
Look at that, yeah.
At the bottom of the tube, there was a bunch more, and to get it out, I just hit it while it was upside down.
Powdery.
So from this, it all clearly worked, and the liquid nitrogen was definitely able to freeze the CO2. I now knew how I would burn the diamonds and collect the dry ice, but after this, I had to somehow use it to carbonate water, and this would have to be done under pressure. I'm sure there are many ways that this could have been done, but what I wanted to do was to somehow use one of those kitchen soda makers. I mostly wanted to do this because I just kind of thought it was funny, but also I thought that it would be really satisfying to be able to see the diamond CO2 being shot into the water. To set this all up, I'd have to build some sort of pressure chamber and somehow rig it to the soda machine. I also wanted to make it as simple as possible, and after about a week of just tinkering with different ideas, I came up with something I thought would work. Overall, it was relatively simple, and I was able to buy all the parts that I needed online from a company called McMaster Car. All the parts arrived a couple days later.
About a simple pressure chamber arrangement you can have.
To lay out the basic setup. On the left was the main pressure chamber, which was basically just a pipe, and on the right was the pressure gauge, and below that was the valve. The idea was to throw the diamond dry ice into the pipe, then quickly seal it, and let it slowly turn back into CO2 gas and pressurize the chamber.
It's interesting that it's the same basic fundamental physics that a pressure chamber, say, at a nuclear power plant has. Albeit, the types that use CO2 were a very old design. This Magnox reactor was a very old school design that used graphite as the moderator, yes, just like Chernobyl, and carbon dioxide gas. This was one of those weird first generation nuclear reactors where your goal is, I want to make electric power, and I also want to produce a lot of plutonium-239 for weapons production, because this was early in the Cold War, meaning let's build a lot of nuclear weapons. Needless to say, that is not a current design consideration for nuclear power plants. But other than that, this works very similar to any other nuclear power plant. Reactor's your heat source. Your gas is the coolant and working fluid. The graphite slows down the neutrons, allowing fissions to occur. It circulates through a loop. That loop is in a heat exchanger with water to create steam and produce electricity, much in the same way electricity has been produced over the past 200 years using a steam turbine. This has some advantages in that you can refuel this reactor while being online, actually kind of similar to an RBMK. But I would argue this design has some limitations. The idea of a gas-cooled and much like the air-cooled reactor from the infamous Windscale accident, it's just not as effective at absorbing heat as water, and it leaves the reactor potentially quite vulnerable in case of a fire. It's just an overall less safe design than having water, which is both as a coolant and as a moderator. Graphite has limitations as as a moderator, well, I go into more detail about that in my Chernobyl review, but it's subject to neutron embrittlement and degradation, which lowers its overall efficiency as something to make the fission process better. And gas also just limits the maximum temperature, so the same thermodynamic efficiency that exists at any other thermal plant, well, you can't make it as hot, it's just not going to be as efficient.
All the metal here was 316 stainless steel, and it was rated at 3000 psi, which was way higher than it was ever going to get to. At most, it would never even get above 1000, and if it ever even got close to 3000, it would probably mean that the entire room was on fire. To put together most of it, I just wrapped each of the threaded pieces with Teflon tape, and I screwed them in.
Even if that was the case, I don't know if it'd get pressure that high, but, well, I don't know what kind of room he's working in. If he's in a bunker, if that's where his lab is, then sure, you can get some pretty crazy pressures there.
The only tricky part was this last end cap piece, which had no place for me to screw into. So to attach the pipe to the rest of the setup, I had to make a threaded hole myself. To do this, I started by drilling a small pilot hole in it. Then, I replaced the small drill bit with the bigger one that I actually needed.
What I love especially about NileRed's videos is how even him just using all these tools, and even if he describes it's a silly process or an experiment or whatever, it's shot so elegantly that it's like each thing is like a work of art, like just the drill bit going smoothly through there. It even makes it a bit more jarring when he takes a hammer and, you know, smashes a beaker or a flask or something. It's a very different look compared to, say, Styropyro, which is all crazy everywhere. I love watching both. I'm a big fan of what they both do. It's just an interesting distinction. It's the first thing that comes to mind between those two.
And I kept on drilling. After taking out a small amount of metal, I added some soapy water to help keep things cool. To hold the end cap, I was just using a cheap plastic clamp, which really wasn't very ideal. It wasn't able to hold on to it very well in general, and with the soapy water, it really had a tendency to spin. However, this didn't turn out to be a huge deal, and it was still relatively easy to drill the hole through it. Now with a hole in it, the next step was to make the threads using a tap. It was important to screw the tap in as close to vertical as possible, and one trick to do this is to load it into the drill press and then to manually turn it. When I felt that the tap was deep enough, I loosened it, and I took the whole thing from the press. I then clamped it down in my vise, lubricated it with some cutting oil, and I started turning the tap. As I turned it, it was cutting away the metal and making the thread, but the deeper that it got, the more force that it took. Initially, things seemed to be going pretty well, but I somehow ended up damaging the tap and ruining its threads, so I had to go out and buy a new one. They're relatively cheap though, and I got the replacement for about $5. Eventually, I felt that I had carved out the threads deep enough, and at this point it was done. I then quickly cleaned the cap and all the threads, and now I was ready to finish putting everything together. I started by clamping down the part with the gauge, and I screwed on the cap by hand. And after that, using a pipe wrench, I really tightened it down. With this upper part of the chamber now ready, I just had to do a quick test to make sure that it all worked. I clamped down the lower pipe part, dropped in some dry ice, and then quickly screwed on this upper section. The dry ice was slowly turning back into CO2 gas, and with everything sealed, the pressure was slowly increasing. I then shot some soapy water onto it, which would start to bubble if there were any leaks.
Okay, yeah.
At this point, it all looked fine, but there was still barely any pressure in it, so it wasn't that surprising. As the dry ice was turning back into a gas, it was cooling down the pipe a lot, and it caused most of the water on it to freeze. To properly test...
It's interesting dealing with the other extreme of the temperature spectrum. I remember we would have technicians do leak checks in the turbine building, and you'd often find some of the steam leaks would be superheated. That is to say, heated above saturation temperature, where liquid turns into gas. And the spooky thing about superheated steam is you can't see it. Whereas saturated steam, you could see these the common puff that you would see, and that's because, hey, it's the liquid turning into gas. But when it gets heated above it, you can't actually see it, and it can burn you. So, again, you really have to use your ears and your eyes in a different way other than just looking. You really have to use your ears. Only thing is, it's a high noise area. So being slow and methodical is key when you're looking for leaks. Granted, you know, there are indications you can use, say such as alarm functions if it's a big enough leak, to allow to have people say, hey, this is where I think the leak is based on what this is doing, what steam flow is doing in one area. But the thing is, for something as large as a nuclear power plant that deals in megawatts, megawatt of steam is a lot. So much of the tiny leaks are so small they probably won't even register. So you just have to be quite careful. Now, steam leaks aren't common. They're not, but at least not significant ones, but it's just another hazard that is routinely briefed when you're working in the turbine building.
Instead, I was going to have to wait for all the dry ice to disappear and for the whole thing to get back up to room temperature. It ended up maxing out at around 600 or 700 psi, and I shot the soapy water on it again. Pretty much all the joints still looked good, except for the one next to the valve, which was clearly bubbling. This just meant that it wasn't tight enough, and I'd have to screw it on a bit more. The test was now over, and I opened the valve to let everything out.
There it goes.
After fixing that valve connection, this was going to be the final pressure chamber, but at the last minute, I decided to modify it a bit. When designing it, I didn't really feel that I needed a pressure release valve because the metal was rated way higher than I was ever going to be putting it at, and also, I was going to be emptying it very quickly after filling it.
Unfortunately, the nuclear industry wouldn't let you do that. There's a certain pressure thing. There's even certain state pressure codes, just boiler codes. I mean, after all, a nuclear reactor is just a really big boiler that specify what type of pressure relief system you have and how many redundant pressure relief valves you have, both power operated relief valves and the spring loaded safety valves. The power operated ones require an electrical signal to function, either remotely or manual operation from the control room. But the spring ones, it's just pure pressure is gonna open the valves. For something like this, obviously it would make no sense to have anything like that. be more than the little piece of equipment is worth, but I just got a chuckle out of that.
The only way that it would ever get overpressured was that if it somehow fell into a fire or something, but that really wasn't very likely. However, despite all that, I decided that it was still important to do things safe and properly. So, I picked up a release valve that would pop if the pressure ever went above 2,000 psi.
Okay, there you go. That's exactly like the safety valves I was talking about. Ones that pop at a certain threshold rather than manual operation or electrical operation.
To modify things, I just had to swap this T-joint that I had with a cross and screw on the new valve. After that, I tested it with some dry ice to make sure that there were no leaks, and I didn't see any, so the chamber was good to go. Now, the very last thing that I had to do was figure out how to connect it to one of those kitchen soda makers. I decided to go with the SodaStream brand, and it was all relatively easy. All I needed was a small section of high-pressure hosing, 2 quick-release adapters, and another adapter
this simple design,
to screw
that's
into
something
the
I love,
SodaStream.
just as an engineer.
I was able to find all these parts on Amazon, which was convenient, but they were all kind of overpriced. For the actual SodaStream, I just went out and bought whatever was the cheapest model. To set it up, I took off the back, screwed in the adapter,
never actually used one of these. I'm not a soda
and connected
person.
one side of the hose to it. To attach the pressure chamber to it, I cut a small hole in the side and slid in a zip tie. I figured that the best and easiest way to hold it there was to just strap it to the side of it, and it seemed to work pretty well.
Right?
I then attached the other end of the hose to the valve, and the setup was finally done. I did a few quick tests to make sure that the system wasn't leaking or anything, and it all seemed to be good. So now, I guess I was finally ready to try and make the diamond water. For the burning setup,
Diamond water.
I started by adding the quartz tube, and this time, I actually clamped it down instead of just balancing it. I then attached a bubbler with a small amount of water in it, which would wash all the CO2 gas that was made. This would probably add a bit of moisture to it though, so I followed this up with another bubbler that was filled with a drying salt. This was then fed directly into the test tube in the dewar from before, and I started loading up the quartz tube with all the diamonds. After all my little tests and some other things,
the way he puts it in there with a super long spoon.
Diamond left, and I decided to just use it all. When this was all eventually done, I sealed the end with a stopper that was pre-fitted with the oxygen feed. I then opened the oxygen tank, and I carefully adjusted the flow of it by looking at the water bubbler. The main purpose of the bubbler here was to wash the gas, but it was also really useful to gauge how much of it was flowing through the system. When I felt that it was going at a good and steady rate, I filled the dewar with some liquid nitrogen.
That's cool, it's effectively a rotometer.
I started blasting the diamonds with a torch. Like before, the diamonds slowly started glowing bright red, and I could tell that they were reacting with the oxygen. They were definitely burning and turning into carbon dioxide, but I didn't see any dry ice forming, and this kind of concerned me. I knew that there was a bunch of oxygen that first had to be pushed out of the system before the CO2 made it there, but I wasn't sure if that was actually what was happening. It was also possible that maybe I had a leak, and I was somehow losing all my precious diamond CO2. I honestly started to get a bit worried about it, and I thought that this might be just a total failure, but then it actually started working. Along with all this nice dry ice though, unreacted oxygen was also getting liquefied.
It could be that he just had a lot of the diamond right there.
I initially thought that this might have been a problem, but it actually turned out to be a good thing.
Keeping the temperature
it stopped the dry ice from clumping up and solidifying on the side, and from potentially blocking the tube.
You see that sometimes, like the difference between like individual. The way I see it, it's somewhat similar to when, you know, you start boiling water in the kitchen, and then it takes a while, and then suddenly goes quickly like that. It's funny how things tend to behave in groups. Also, main reason due to latent heat of phase change being the barrier before any further heating, that, you know, you kind of see stuff act in groups like that. There's a lot of terms for boiling in a nuclear power plant that talk about like what types of boiling.
I initially thought that this was just going to take something like 10 minutes, but the whole process was over an hour, which kind of killed me. The reaction that was going on here was quite simple, and the diamond, which is nearly pure carbon, was reacting with the oxygen to make CO2. As this reaction happens,
looks like it gets faster as you have less of it.
Disappears, and when it's done, it should pretty much be all gone. Even in very pure diamond, though, there's always still a small amount of impurity in it, which is going to be left behind.
That's what that dust is.
I purposely went with white diamond because it's one of the most pure forms.
So that's true even when boiling water in steam generators in a nuclear power plant. It's highly purified, but there's still a little bit. It's no different, again, going back to your kitchen, you know, your tea kettle. You have a little bit of minerals left at the bottom after you've used it for a while, and that's what's left over. There is a system for that in a nuclear plant called the steam generator blowdown system that takes those little things that have accumulated on the bottom, has a purification loop that sucks water out and purifies it, and that gets your secondary loop. So the secondary being the non-nuclear part of the plant that just feeds the turbine. This sort of thing exists outside of nuclear as well, by the way. The difference is that in case of primary to secondary leakage from the reactor to the secondary plant, it has additional isolation systems as well as radiation monitors that on high radiation would isolate it so you don't send radioactive materials out to the turbine. And ultimately, you don't dose the public with radioactive isotopes. So it has an emergency system associated with that as well, but an emergency purification system associated with radioactive materials. Its normal function is to clean out your impurities.
A lot of other diamonds can be slightly colored from impurities, and they probably would have been fine to use. However, I just wanted the CO2 to be
There'd just be less gunk. There would be more gunk in there if you used that.
As I could. When it was done, I took out the tube, and there was a lot of dry ice at the bottom, but there was also a whole bunch of liquid oxygen. To get rid of the oxygen, though, it was easy, and I just had to shake the tube around and let it all boil off. As I did this, it slowly sounded more and more solid, and eventually, all I had left was the dry ice.
Diamond ice.
At this point, I was planning to just throw it directly into the pressure chamber, but I really wanted to see how much I got. On something warm, though, dry ice would sublime really quickly, so to minimize the loss, I made a really cold watch glass. I was able to pour out pretty much everything that was in the tube, and I was honestly surprised by how much dry ice there was. I was also just really happy that this project seemed to be working.
Now, I know you zoomed in, but it looks like there's more of it than initially. I mean, that's because, you know, diamond is ultra dense, and this is less dense. Even though there's overall less material because there were impurities left behind. But, yeah, that's pretty good.
And I was genuinely still kind of blown away that this all came from diamond. I weighed the tube before and after I poured it out, and my yield was 10.5 grams, but in theory, I should have gotten around 12.8.
Okay.
I think that some of the CO2 was missing, though, because it was able to get out of the tube before getting frozen by the
leakage plus impurities.
There also could have been leaks in my system, and I could have also lost someone trying to weigh it. Either way, though, I still had way more than I needed, and the next thing that I had to do was load it all into the chamber. I just dumped it all in as fast as I could, and I quickly screwed on the cap. The pipe that I used for the chamber here was also a lot smaller, and it was because I scaled it based on the amount of dry ice that I got. All the dry ice slowly vaporized over the course of about 15 minutes, and the pressure got up to around 800 psi. I waited another half an hour just to make sure that all the dry ice had turned back into a gas, and it was pretty much good to go. I now had this weird cross-looking pressure chamber thing, and all I had to do
like an action
was
figure.
Attach it to the soda stream. Because the chamber was much smaller now, I had to make a new hole for the zip tie. That didn't even take a minute though, and then I clamped on the chamber, attached the tubing, loaded a small bottle filled with cold water, and opened the valve. I was now finally...
The cross with a little pin on its left arm, like that. The head is the gauge, and it's got a little pin, like some sort of robot arm that you pull out and things happen. I mean, it would be pressurized, but yeah.
Ready to make my diamond water, but I was honestly pretty nervous because I really felt that I was gonna somehow mess it up. After a few minutes of psyching myself up though, I just went ahead and pushed the button,
there you go, buddy.
The diamond gas started flooding into the bottle.
Look at that. All bubbly. Diamond bubbly.
When I felt that it was done, I took it off, and a bunch of bubbles formed the moment that the pressure was released. I made sure to quickly cap it though, to try and lose as little of the gas as possible. To make this bottle, I pretty much used all of the CO2 that was in the chamber, but there still was a very small amount of it left. Unfortunately though, this wasn't enough to carbonate anything else with, and I just decided to keep it. I thought it was cool to still keep a small amount
extra
of
diamond gas
too, but I don't really have any purpose for it. But anyway, now, after spending over $1,000 and weeks of working on this, I was finally done. As far as I could tell, I had successfully carbonated water.
Note that a lot of it wasn't on the diamonds directly. The diamonds was just $200, but yeah, pressure chambers, a good regulator, yeah, that stuff will run you as well as liquid nitrogen. So if he would have used graphite, it wouldn't have cut the cost very much.
Diamonds, and I was honestly surprised that it worked this well. At over $1,000 for this bottle though, not even counting labor, I still wasn't sure if it was actually worth all the work and money. However, I was really hoping that once I tasted it and experienced the amazing flavor of diamond CO2, that all those doubts would disappear. Okay, so it's finally time to taste it and to see how it is. So,
one interesting thing about diamonds is There's currently this experiment involving maybe making a nuclear diamond battery. And it would use carbon-14, because after all, like you said, diamonds are just carbon in a very interesting lattice formation. And carbon-14, that's the same isotope used for radiocarbon dating to look at its half-life and determine how old various historical artifacts are. And this works just by producing power from radioactive decay, kind of like RTG, that's radioisotope thermoelectric generator, act as a propulsion source for spacecraft. Now, this is spacecraft that's already in space because it produces very small amount of thrust. But when you're in space, you don't need much. You just need something small and consistent that can last hundreds of years, which is what those things do. But the interesting thing about carbon-14 is its half-life is over 5,000 years. Now, this is still a way off, but that could be pretty cool, just having something that lasts a while. Funny thing for me, I can't stand anything carbonated, so I'd probably just spit it out. Even when I was a kid trying soda or whatever, I just can't stand it, so better him testing this than me.
Tastes, exactly like soda water. Weeks of work to have something
that's funny,
indistinguishable from regular soda water.
Carbon is carbon?
It's honestly kind of worse than regular soda water because I just used tap water and pass it through a Brita filter before carbonating. I didn't even think of using better quality water. And the tap water at my office, here, kind of tastes horrible on its own. The Brita recovers a lot of the flavor and makes it not taste absolutely terrible, but the Brita makes it taste okay. But in hindsight, I should have used something better. And now it just tastes like either just regular soda water, maybe slightly inferior. But knowing that it has diamonds in it, or diamond CO2 in it, makes it inherently better still.
It does. It has to be that whole placebo effect. Market it as diamond water, and then people will, talk about how refined it is, even though it's effectively the same thing, just because that's what they believe it to be.
Okay, so it turned out to be no different than regular carbonated water, and I actually expected that to be the case. Carbon dioxide is just carbon dioxide, and it doesn't matter if it came from diamonds or from burning something like gasoline.
Yeah.
It's always just going to be CO2, which means it'll have the same chemical properties and the same taste. Despite this, though, I still really like the idea of diamond water, and I'm still blown away by the fact that it works so well.
I love it.
After tasting it, I still had a mostly full bottle of water, and I poured the rest of it into a bunch of small vials. I didn't feel it was appropriate, though, just leaving them as these unmarked vials, so I went out and had some nice custom stickers made.
Yes.
In total, I was able to fill 10 vials, and most of these ended up being given out to friends.
Wow.
I made sure to keep 3 of them, though, which I wanted to give away to you guys. But anyway, I think that's about it for now.
Thanks so much for the recommendation on this one. It was cool just seeing the process, and like I said, I can't say I've ever seen this, and now I can understand why. Very expensive way to make something that already exists, essentially, but hey, the fact that he was able to do this was really cool. Plus, just telling you the geological history of the substance you use to put in your drink is kind of cool, saying this was once diamonds at some point. Thank you very much for watching. I'll see you next time.